Okay. All right, so again, electrophilic addition. Okay. Cool, and HBr. And we said that that bromine is going to go on that more substituted carbon, my secondary carbon. To be clear, I can also show that that hydrogen got added to that less substituted carbon because this is an addition reaction, right? So we can see where everything went. We don't have to include that hydrogen because hydrogens are implied, but sometimes when they're involved in the reaction, it's kind of helpful to see. Okay? All right, so what we want to do to better understand why the bromine is going onto this carbon right here is to look at our mechanism for this reaction. So I'm going to show our bond. I'm actually going to be good and put my lone pairs on my bromine as well. Okay, and we're going to need to introduce some terminology that is hopefully familiar. All right. In every reaction in organic chemistry, we have our nucleophile. Okay? What does it mean? What does that ending "phile" mean? Does anybody know? Loving, right? So a nucleophile is a nucleus-loving species. So this is one that is electron-rich because it loves that positively charged nuclei. And then that reacts with an electrophile. An electrophile is the exact opposite. An electrophile is electron poor. That's why it loves electrons. All right, and this is kind of the basis of all chemical reactions in organic chemistry. We have something with a lot of electrons that's going to be reacting with something that doesn't have a lot of electrons. It has relative electron deficiency, okay? And so what we want to sort of be good at is when we look at these molecules, we want to kind of see in our mind's eye where they're glowing hot with electron density, okay? These carbon-carbon double bonds, that pi bond, has a lot of electron density. So in our mind's eye, we see those double bonds like they're glowing red. They got a bunch of electrons going on. All right? If we look at HBr here, this is a polar molecule. Which one is the more electronegative atom, the hydrogen or the bromine? The bromine. So that means that there's a lot of electron density on this bromine atom. And that hydrogen is left relatively electron deficient. Right? So in like our mind's eye, we have this little heat map of electron density where we see a lot of electron density in that double bond and on that bromine ion. And we see that that hydrogen is cold. It doesn't have a lot of electron density. Okay? Again, that's because this is this polar bond right here between hydrogen and bromine. So if something that's electron rich is going to attack something that's electron poor, we see that that double bond is going to reach out and attack that relatively electron deficient hydrogen, right? Electrons want to move in an area from low electron density, of high electron density to low electron density. Now, I can't stop right there, or I'm going to violate hydrogen's octet rule. Hydrogen's definitely not about to have more than one bond, right? So at the same time, I'm going to have to break that hydrogen-bromine bond. All right, so this brings us to our intermediate for this reaction. Okay, and now we have this question of where that hydrogen's going to go. I can either put that hydrogen on carbon 1. Okay, we're going to pretend like we don't know the answer yet. Or I can put that hydrogen on carbon 2. All right, and before I can figure out which one of these intermediates is correct, I'm going to put my bromide ion in there as well, right? To be clear, bromine, since it accepted this pair of electrons right here from that bond, it's now got that extra lone pair on it. Right? We got to conserve our electrons. They're always going somewhere. Okay, I'm not quite done with my organic intermediate though. What's missing? Charge, right? So let's just look at our conservation of charges. Everything's neutral in this first step. I have this negatively charged bromide ion. There's got to be a positive charge somewhere in that intermediate step. So absolutely, this pair of electrons, it got taken away from this carbon atom and given to the hydrogen. So I have a carbocation right here in my first intermediate. Or if hydrogen was placed on that second carbon, that means this first carbon got its pair of electrons taken away. So there's my intermediate. All right? And so distinguishing between these two is how we know which one our product is. All right? So we're going to remind ourselves about carbocation stability. All right? The one you'll never see, a methyl carbocation. That is the least stable. All right, and from there, it increases in substitution. All right, a primary carbocation followed by a secondary carbocation, and then our most stable tertiary carbocation. All right, so which one of these intermediates is going to form? If I look, this one up here is a secondary. This one over here is a primary. All right. Secondary beats primary in terms of our increasing instability. So this is going to be my actual intermediate. This primary carbocation right here will not form. Okay, so everybody take a second. Now that we know what our intermediate is, finish off this reaction mechanism, right? Our bromide and our organic intermediate here are going to be involved. Okay, so finish off that mechanism for me. All right, and I am leaving a little bit of space over here because we're going to add to this list here today. Okay, I'm going to get rid of all this noise here. I need to draw another electron pushing arrow. Is it going to be a bond breaking arrow or a bond formation arrow? I need to create this bond over here on my product side, right? That's not existing over here. So how do we create a bond? We're going to start at a pair of electrons and end at this carbocation that is accepting that pair of electrons. All right, so that is my new bond being formed. This mechanism here actually has a good illustration of these three different categories that we talked about. Like we said, this one was bond formation. Okay, we also have a bond breaking arrow here because it starts at a bond and ends at that bromine atom accepting that lone pair. And then we have one that does both because it starts at a pi bond, bond breaking, and formation. So those are those three categories that we had discussed of our reaction mechanism arrows. Cool. All right, so this would have been one of the first addition reactions that you would have studied. Again, addition because you're adding both the H and the Br to your organic molecule. All right, and we had this Markovnikov, this selectivity, where the bromine specifically went on the more substituted carbon. And it went on the more substituted carbon. The way that we explain that was by looking at our mechanism here. A carbocation has to form somewhere in that molecule. It's going to form on the more stable position, which is the more substituted carbon. All right, so now we're going to look at this reaction with a conjugated diene. Okay, remember, in order to be conjugated, those pi bonds have to be spaced out perfectly so that we have a row of sp2 hybridized carbons all in a line here. Right? That perfect double bond spacing. Again, we're talking about electrophilic addition. Okay, and I lied. We're going to go back real quick, and we're going to think here, because we introduced this terminology and then never used it. In this first step here, what is playing the role of the nucleophile? What is my electron-rich species attacking something that's electron-poor? The double bond is going to be my nucleophile. And what is the electrophile going to be? That relatively electron-deficient hydrogen. But then let's look in our second step here. So first of all, what should be glowing red hot in this second step here? That bromine, because now it's a bromide ion. It's got an extra pair of electrons. I mean, one thing that definitely makes a nucleophile is having this net negative charge associated with it. That's a lot of electron density. All right, and then is anything glowing blue here? That carbocation, because now that carbocation is relatively electron deficient. It's got a positive charge associated with it. Whoops. So then what would be my electrophile in this second step here? Carbocation. All right, so my bromide ion is playing the role of the nucleophile in that second step, right? Nucleophiles attack electrophiles. We use that verbiage over and over and over again. Okay. Cool. So conjugated diene, we're going to play this same game with a molecule of HBr. All right, I want y'all to take a second and see if you can't give me the first step in this reaction here, because it's the exact same as our other one, right? What's our mechanism here? First step in our mechanism, I should say.
A double bond attacks hydrogen.
Yep, totally. So drawing your electron pushing arrows. Let's make sure that we're starting in the right place, ending in the right place, all that stuff. Yes, we have that same nucleophile attacking that same electrophile. Again, my nucleophile is going to attack that electrophile. Got to break that bond there. Okay, so there's my electron pushing arrows. If you've not already, draw the intermediate of this reaction. All right, so then let's think about it. Now my carbocation is relatively electron deficient, and this bromide ion has a ton of electron density. So take a second and see if you can't predict what's going to happen in this next step and what our product would be.
Does the intermediate need one more double bond?
Yes, it does. Sorry. Yeah, then nothing happened to that other one right now. Okay, So we have that first double bond that we didn't touch. We have hydrogen added over here. And now that bromine is going to have attacked that carbocation, forming this new carbon-bromine bond. All right, so far nothing crazy. So far exactly as what we just saw for our electrophilic addition to alkenes here, okay? This is what we would call the 1,2 adduct. It's our addition product, so we call it an adduct, and we call it the 1,2 because hydrogen is located 2 carbons away from that bromine. All right, and indeed, this is one product that we can get from these electrophilic addition reactions, but it's not the only product that we can get. All right, because if we look at our intermediate again, yes, we got that carbocation glowing blue, that bromine can attack, but we also got that double bond. And what color should we color that double bond? Red, right? So that's another pocket of electron density. So our bromine can attack that carbocation, or we can have a resonance rearrangement within this molecule where that double bond pair of electrons goes and attacks that carbocation. All right, everybody take a second. This would now be a resonance arrow. I'm going to use this double-headed arrow. Everybody take a second and draw me the product of this step right here, following these electron pushing arrows. All right, so importantly, that hydrogen is not going to move from carbon 1. It's still there. What do I need to fill out my intermediate here? What's missing? So I have a double bond. My double bond swapped positions here. So now my double bond has moved to be between these 2 carbons. All right, and what else am I missing? That charge, right? So the double bond and that carbocation, they kind of swap positions, right? This carbon now has that pair of electrons taken from it, okay? And so now I have my carbocation over here glowing blue. My bromide ion is again floating around in solution. So we can get one other product here as a result of this resonance rearrangement. All right, I'll put in these electron pushing arrows and I want you to follow them for me. This bromide is going to attack that carbocation. Okay, so now my bromine is located all the way on the other end here. This is what we would call the 1,4 adduct. Because these 2 are located 1, 2, 3, 4 carbons apart from one another. All right, so we have these 2 possible products of this electrophilic addition reaction. The one is our normal old one that we would expect just given the behavior of how alkenes react with these electrophiles. And the other one that we have as a result of our resonance here, right? So that's what this part right here was, our resonance of those conjugated pi bonds. Okay? Now, looking at these two intermediates here, if we were to apply our kind of like old rules for carbocation stability, what would we say about which one would be more stable? The top one, right? Because it's more substituted. All right, it turns out that there is something way more important than degrees of substitution in terms of stability, and that is that resonance stabilization. So all the way at the tippy top of our list over here, we're going to put this allylic carbocation. Right? Remember, allylic is what we call that position that is one removed from a double bond. Because of that resonance stabilization that we just illustrated with those resonance structures, allylic carbocations are way more stable than all the other carbocations of the world. So this is our most stable. All right, so this is going to be really important when you're drawing your intermediates for these reactions. You're not going to be focused on always putting it on the more substituted carbon. You're going to be focused on always putting it on the allylic carbon, right? That's where your double bond is going to be. I'm sorry, that's where your carbocation is going to be. Okay, so let's just do another example just to kind of hammer this home here. All right, I want everybody to take a second and draw me the mechanism specifically for that 1,2 adduct. With HBr. Right, so that pi bond is going to reach out and grab that proton. I'm going to be left with a bromide ion. All right, I again have my carbocation intermediate. Okay, but my point in this example is to try to hammer home here. Which position should our carbocation be on? The red position or the orange position? Yeah, regardless of the fact that there was some confusion out there. All right, so regardless of the fact that orange is the more substituted carbon, what trumps substitution in terms of our degrees of stability? Being in that allylic position, right? So the red carbon is where I'm going to put my carbocation, because I don't want it to be too far away from that double bond so that it can't talk to it anymore in resonance, right? It has to be in the allylic position. My hydrogen will be over here on this one. Okay, so again, Whole point here, illustrate carbocation, always allylic. All right, so then if we're going to finish our mechanism here, my bromide ion, let's not make it red because that's not what we want. It's glowing blue. Is going to attack that carbocation. Okay. So just like we saw for our regular addition to alkenes, we're going to have this carbocation intermediate. Again, just like we saw with our regular addition to alkenes, the carbocation is going to form on that more stable position. But now that more stable position is always going to be an allylic position, right? Because that's even more stable than worrying about degrees of substitution. Okay, so let's just summarize real quick. Just looking at our chemical equation here. We have our conjugated diene plus that electrophile. And we have two potential products here. The first we call the 1,2 addition because hydrogen and bromine are located 2 carbons apart. And the other one we call the 1,4 adduct, 1,4 addition, because the hydrogen and the bromine are located 4 carbons apart. Okay, so these are 2 possible products that we get from our electrophilic addition of conjugated dienes. Again, 1,2 because they're 1,2 carbons apart, 1,4 because they're 1, 2, 3, 4 carbons apart. All right, what other big difference can we notice about these 2 products if we're just looking and playing the spot the difference game here? Yes, the bromine's in a different position. What else is in a different position? The double bond, right? Because of that resonance that I used to get to that 1,4 addition, let's just note that our double bond has also moved. All right, we can even note because of resonance. All right, so it turns out that we can kind of tune the conditions of our reaction to give us one product over the other one here. All right. If we conduct this reaction at low temperatures, our distribution of products would be like 90% 1,2 and 10% 1,4, where if instead we cranked up the heat, we get the exact reverse. Now all of a sudden our minor product is the 1,2 and our major product is the 1,4. right? So we can tune our reaction here using temperature to give us one over the other, all right? So why is that? Okay, also these numbers I made up, bottom line, major, and minor. Okay, so in order to sort of better understand what's going on here, we're going to have to review another thing that would have been sort of covered many times in chemistry. We love using these energy diagrams. Okay, so we're going to create this little graph here. Where on our y-axis we have energy, or more specifically in this case, we're going to use free energy. And on our x-axis we have our reaction progress. Okay, so these are these little curves that look something like this. All right, we always start out flat over here before any reaction has progressed. And then there's this little hump in the middle, and then they flatten back out at the end here. All right, over here on the left-hand side, this is the starting energy of my reactants. Right. Then as my reaction progresses, the energy increases before finally I get a release of energy as my products are forming their new bonds. So this is the energy level of my products. All right. There's kind of two big pieces of information that we can get from this chart. One is by looking just at the endpoints. So looking at where the reactants are relative to the products, right? So this gap right here would tell us our delta G of our reaction. All right, in this case, because my products are less energy than my reactants, this would be a negative delta G. Okay, but the first piece of information that we get from this graph here, we call our thermodynamics. And again, we only look at the endpoints to get information about the thermodynamics of this reaction. Right, so the difference between our product and reactant energy. All right, but we also get another piece of information. So the thermodynamics are just looking at the endpoint. We get other information by looking at what happens in the middle here, the height of what we call our activation energy barrier. So looking at my reactants and now measuring up to this transition state right here. This is our activation energy. And this tells us about the kinetics of the reaction. By kinetics, we mean how fast. Okay. And so what would represent a fast reaction? A reaction with a small activation energy barrier or a large activation energy barrier? Small, right? So how we kind of imagine this is our reactants are sitting over here with a certain amount of energy, and they need to jump over this activation energy barrier to get to the product side. The higher that barrier, the harder of a time they're going to have, the more energy they're going to need, right? So our kinetics are also illustrated in this. Oops. right? The height of that activation energy barrier. Okay, and let's kind of just summarize what we said for kinetics here. Right, a small activation energy barrier is a fast reaction. A large activation energy barrier is a slow reaction. All right, with regard to thermodynamics, that delta G value. So first of all, what's good? Positive delta G or negative delta G? Negative delta G, right? Okay, cool. So then what would correspond to a more thermodynamically favorable reaction? One with a teeny negative delta G or one with a large delta G? Right? So the bigger that gap in energy between your reactants and products, the more that equilibrium favors the product side. All right, so for thermodynamics, a large negative delta G is a very favorable reaction. A small negative delta G is a less favorable reaction. Okay, so we're going to try to use this free energy diagram here, these diagrams, to help explain why we have these differences in our product distribution. Okay, so let's take our same reaction here, and now I'm going to make a free energy diagram. So I'm going to draw the reaction, the free energy diagram for this 1,2 adduct in blue here. All right, I'm going to start here. I'm going to draw my activation energy barrier and then have it level off here. So again, that's for my 1,2 adduct in blue. Okay, now on top of that, I'm going to sketch the same thing, my free energy diagram, but now for that 1,4 adduct. All right. Importantly, this is going to have to start in the exact same place because my reactants are the exact same. All right, so both of these graphs start in the same place. Okay, but now for my 1,4 adduct. Because I had that resonance step, my activation energy barrier is going to be a lot higher than it was for my 1,2 adduct. Okay, but I get this more conjugated, or rather more substituted alkene at the end. So my 1,4 adduct is going to end at a lower energy than my 1,2 adduct. So in terms of my activation energy barrier here, which one of these is the faster reaction, the 1,2 or the 1,4? The 1,2. So this is what we would call our kinetic product. Your kinetic product is the one that's favored at low temperatures. And it's called the kinetic product because that's the one that forms the fastest. Okay. But if I'm looking at my thermodynamics here, if I'm looking at the beginning and the end points here, which one of these reactions is more thermodynamically favorable? Red or blue?
Red.
Yeah, which one has that bigger free energy gap here, right? So my blue, my delta G is from here to here. My red, my delta G starts out in the same place, but now ends all the way down here. So I have this bigger free energy gap for that red curve. So this is what we would call our thermodynamic product. All right, this is what forms at higher temperatures. Okay, and it's the one that is the more stable of the two. Cool. All right, we're going to leave it there. I'm not going to try to rush through the rest of this. We'll have to pick up with this next time. Cool.